2017 AP Calculus, AB, number 1, calculator active. Let's read. A tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. Okay, so the area of the cross-section of this tank, there's a three-dimensional tank coming off of this paper, and the area of the cross-section at any given height h is given by the function a of h. Good to know. So that means that whatever shape this tank is, it's not going to have a consistent cross-sectional area as we can see. So if you're trying to visualize this, just look at this for a second. At the base of the tank, when height is 0 feet, you have an area of 50.3 square feet, and at the top you have an area of 2.9. So it's probably like an inverted funnel type thing. Okay. The function a is continuous and decreases as h increases. So a is continuous and decreases as h increases. That's going to come in handy later. They gave us selected values of a of h in the table. And part A, use a left Riemann sum with 3 subintervals indicated by the table to approximate the volume of the tank, indicate units of measure. Let's go. All right. Left Riemann sum means I'm going to be dealing with, well, rectangles that are based on the left number, so 50.3. The width is 2, 50.3 is the height. So 2 was part A, times 50.3 plus 3 times 14.4, 3 times 14.4 plus 5 times 6.5. Okay, let's go ahead and crank out an answer. And when we do, we also need to figure out what we are figuring out. Let me rephrase that. We need to figure out the units of it, so we need to put this in context. So 2 times 50, 50.3, 3, 14.4, 5, 6.5. Everything right? Yep. 176.3. Okay. They wanted us to approximate the volume of a tank. The volume of a tank is measured in cubic feet in this context, so this would be cubic feet. Okay, part B. Does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Okay, we have a function that shows the cross-sectional area as a function of height. We have a function that is continuous and decreasing. And with a decreasing function, a left Riemann sum will be an overestimate. If you need a visual for this, and this is not part of my work, but if you need a visual for this, it would be basically a decreasing function. And drawing little rectangles here for a decreasing function would give me an overestimate. So if you need a visual, you can draw it, but the actual answer is right here in words. The approximation. You could say the approximation from part A, the approximation of 176.3, the approximation of 176.3 cubic feet is an overestimate because A of h is a decreasing function. Part C. The area in square feet of the horizontal cross-section at height h feet is modeled by the function f given by this. Okay, now you might be saying, well, haven't they already told me the values? They told you the values, but now we're modeling it in a different way with a different function. Based on this model, find the volume of the tank, indicate units of measure. So what we're going to do is basically add up an infinite number of areas to find volume. So we're going to accumulate area and get volume. So the integral from 0 to 10 of our function. So 50.3 over e to the 0.2 h plus h, and then dh. So this is the area at any given value, h, and if we added up all those areas, we would get volume. So let's do it. Good thing this is calculator active. From 0 to 10 of 50.3 divided by. Now this denominator is a binomial, so we need to make sure that we put it in parentheses. I'm using x instead of h, totally okay. Make sure everything is typed in there correctly. And 101, there we go. 101.325, let's put some units on that. And they did say indicate units of measure, so we did that. Let me also point out here that the approximation was an overestimate. Sure was. Just saying. All right, here we go. Part D. This is where things get fun. I mean, just in case you weren't having fun already. Water is pumped into the tank. Okay. When the height of the water is 5 feet, the height is increasing at the rate of 0.26 cubic foot per minute, or foot per minute, sorry. Use the model from part C, find the rate at which the volume, I'm going to stop right there. As you read this, you might start feeling overwhelmed, and when I feel overwhelmed in a problem, when they've given me a ton of information, I like to make a list. So let's do that. Water's pumped in the tank. The height of the water is 5 feet. Good to know. I'm going to keep reading. The height is increasing at a rate, so dh, dt. Oh, here we go. This is starting to look like related rates of 0.26 cubic feet. Sorry, just feet. Cubic feet is volume. This is just regular standard feet. Okay, feet per minute. And then using the model from part C, what model? This equation right here, this function that they say, you know what, this is a really good fit for this data and the actuality of this tank, this 10-foot tank. So we're going to deal with, well, basically the volume, which goes from 0 to the height of f of x dx. Whoa, what just happened? Okay, I pointed at this and I said we're going to use this. Yeah, we're going to use this and the accumulation of that. We want to deal with the volume using the height, the accumulation of the areas with a given height. This is it. Okay? So we're going to have to take the derivative of this. All right, so from 0 to any given h value of our f function, which they gave us in part C, and we're going to go from there. Let's keep reading though. Use that model. Find the rate at which the volume of the water, so dv dt equals what? Is changing with respect to time when the height of the water is 5 feet. Okay, we're going to take the derivative of this, and this is related rates with a little twist. So it's related rates with the second fundamental theorem of calculus, which really means we're going to take the derivative of an integral. Sometimes it's called the second fundamental theorem of calculus, sometimes it's called something different, but basically f of h, but we also need dh dt. Okay? All right, let's keep going. We're going to plug in everything we can and figure out what they're asking us for. Oh, by the way, in case you have no idea what just happened, the derivative of an integral, so h would go there, but we also have to take the derivative of h, which is where this came from. So dv over dt is f of h. Well, that would be f of 5, and then dh dt is 0.26, and we need to figure out what all this is. So we're going to find f of 5, and it's going to be super easy because this is calculator active. So let's type it in, clear out whatever we have, and we're going to have 50.3 divided by, parentheses again, e to the 0.2x, and then plus x again. And we can plug in a 5, multiply by 0.26, and we'll be done with it. So alpha trace y1 retrieves that, plug it in a 5, that will calculate this, and then we're going to multiply by 0.26, and we have this number right here. 1.694, And they did say indicate units of measure. And the units of measure of what? Well, this is a rate of change of the volume. Volume in this case is cubic feet. And it's the rate of change of that, so it's cubic feet per minute. Okay, let's grade our paper, see how we did. I better get 9 out of 9. Otherwise, I gotta start this video over. All right, part A. I need the units in part A, C, and D. That's worth 1 point right there. All those things are present and they are correct. So cubic feet, and cubic feet per minute. Cubic feet per minute. Good so far. All right, part A, actually, the left Riemann sum and the approximation itself. Left Riemann sum, and boom, got it. We've earned 2 points there, already earned a point for the units, so we're up to 3 points so far. Part B, I get my overestimate and the reason, that's worth 1 point. So did I say overestimate? I did. Did I give the reason? And here, because the function is decreasing. Yep, there we go. Got it. Here goes part C. The integral and the answer, each worth a point. So here's our integral, here's our answer, and that is the correct numerical answer. So we earn 2 points there. And now we get to the tricky one. This is not the most obvious thing to do, but we have 2 points for dv dt and 1 point for the answer. Now, 2 points for dv dt, what do you mean? So we needed this, which we had. If you use different variables, I think it'd be okay. Well, if you don't have x, but you use some other variable instead, that would be fine. But when you take the derivative, you end up with this. This right here was worth 2 points, and then plugging in the numbers was worth the other.